Chapter 1: The Quiet Giant Beneath Your Feet. Chapter summary: You begin by settling into the idea that the ground beneath you is not solid, but slowly breathing. You are guided into Earth's deep layers like descending into warm, hidden rooms. The planet becomes a living body, patient and powerful. Supervolcanoes are introduced not as monsters, but as sleeping giants. Their silence becomes the first mystery. You rest now in stillness, and you imagine the ground beneath your body. It feels firm, dependable, unmoving. Yet in truth, it is none of these things completely. Beneath your feet, beneath your walls, beneath the quiet roads and sleeping trees, the earth is not frozen stone. It is slow motion. It is stored warmth. It is patient movement measured not in minutes, but in ages. You breathe in, and as you do, you picture the planet breathing too. Not loudly. Not urgently. Just a gentle expansion and settling, like a chest rising in sleep. The crust you stand on is thin, surprisingly thin, like the delicate skin that forms on cooling milk. Beneath it lies heat that has never gone out. Leftover fire from Earth's formation still glows below, and additional warmth is made every day by the soft ticking of radioactive elements deep in the mantle. This is not a flame you can see, but a steady inner warmth, like coals buried under ash. You do not fall through because balance holds everything in place. Pressure presses upward. Weight presses downward. Forces agree, for now, to remain in conversation. As you imagine descending, you move not with fear, but with curiosity. Down through layers of rock formed from ancient seabeds, mountain roots, and compressed time. Each layer is like a page: limestone, basalt, granite, each written under different skies. You pass fossils locked in stone, the shapes of creatures that once breathed sunlight and swam in vanished oceans. Deeper still, the temperature rises gradually. Not a sudden furnace, more like walking into warmer and warmer rooms. The rocks change character. They soften. Under enough heat and pressure, even stone can bend. Over long spans, it flows like very thick wax. This deep region is called the mantle. Not liquid, not solid, but something in between, a slow-moving solidity. If you could watch it for 1,000,000 years, you would see it circulate like a lava lamp moving in sacred slow motion. Heat rises. Cooler material sinks. The cycle continues without hurry. And in certain places, this rising heat gathers. It collects beneath thinner parts of the crust. It pools beneath weak seams and ancient fractures. It melts rock into magma, which is simply rock that has become liquid from heat and pressure. Magma is not empty fire. It is mineral-rich, glowing, heavy, carrying crystals and dissolved gases like breath held in molten form. You might imagine magma as anger or violence, but here you let that idea soften. Magma is transformation. It is stone learning to move again. In rare places on Earth, magma does not just gather in small pockets. It gathers in vast underground reservoirs, chambers so wide they could hold cities. These are not the steep cone volcanoes you see in postcards. These are broader, quieter systems. Their surface expressions can look like valleys, lakes, or gentle highlands. They do not always announce themselves with peaks. These are the homes of supervolcanoes. The word sounds dramatic, but you let the feeling become calm. Supervolcano does not mean constantly erupting. It means capable of a very large eruption if conditions align. Capability is not action. A sleeping whale is still large, still powerful, yet peaceful in its rest. You picture one now not as a mountain, but as a vast underground bowl of warm, glowing melt, miles across, resting beneath forests and rivers. Above it, animals move. Rain falls. Snow gathers. People build homes and sleep through the night. Most of the time, nothing happens. And this is the part that matters most for your rest. Earth prefers balance. Pressure usually escapes slowly through cracks, through small eruptions, through geothermal vents, through hot springs where mineral-rich water rises like warm breath. The planet has many safety valves. Yellowstone, for example, releases heat every day through steaming pools and geysers, like a kettle whispering instead of screaming. You listen to that image, a whispering kettle, and you feel how release can be gentle. Supervolcano systems are monitored carefully by scientists who place instruments like stethoscopes on the land. They measure tiny earthquakes, ground swelling measured in centimeters, gas chemistry changing in subtle ratios. The Earth speaks in signals long before it shouts. And those signals are slow, patterned, and studied with patience. Nothing here is sudden in geological time. Even rapid change underground often takes years. Sometimes centuries. You let your thoughts move at that slower speed now. Imagine pressure building not like an explosion, but like a story being written word by word. Each crystal forming in magma changes its chemistry slightly. Each bubble of dissolved gas shifts the balance a little more. Each movement of mantle heat adds a small paragraph to a chapter that may never be finished. Most supervolcanoes never erupt in your lifetime. Many sleep for hundreds of thousands of years between major events. Sleep is their most common state. You feel the comfort in that. The normal state of giants is rest. Above these systems, landscapes form that are unexpectedly beautiful. Wide calderas, which are large volcanic basins formed by ancient collapses, often become lakes. Soil enriched by volcanic minerals grows thick forests. Life prefers these places. After long spans, destruction becomes nourishment. Ash becomes nutrients. Minerals become roots and leaves. Transformation circles back into growth. You trace your awareness again from the deep upward. From warm mantle currents, to magma chambers, to layered crust, to soil, to grass, to the air touching your skin right now. The distance feels enormous, yet connected like different floors of one great house. You are lying on the roof of a warm, living structure. And it holds you. The idea of a sleeping giant feels different now. Not a threat. Not a monster. Just stored energy inside a living planet that has always changed slowly, thoughtfully, rhythmically. The same earth that grows mountains also grows meadows. The same heat that melts rock also drives the magnetic field that shields your sky from solar storms. Deep power can also be deep protection. You breathe again, and imagine your breath traveling downward like a thread of awareness, touching the warm depths, acknowledging them, and returning calmly to your chest. No urgency. Only connection. The giant sleeps. The crust floats. The mantle turns like a slow wheel. Time moves like honey in the dark. And deeper still, beneath even the magma chambers, The heat continues its quiet work, preparing motion so gradual that it almost feels like silence, and in that silence, something thick and glowing is beginning to drift. You continue your gentle descent, not with your body, but with your awareness. The surface world grows quieter above you, wind, leaves, distant sounds, all fading like evening echoes. Below, there is no noise in the usual sense. No crashing. No roaring. Only pressure and warmth and time moving at its own unhurried pace. Here, fire does not flicker. It flows. You imagine magma not as a burst of flame, but as something thicker, smoother, like honey warmed by sunlight and poured in slow motion. It does not rush unless forced. It folds into itself. It stretches. It gathers. It glows from within. Magma is born when rock melts, and rock melts when heat and pressure work together for long enough. Different rocks melt at different temperatures, just as butter softens before sugar does. Deep below, minerals separate and blend, forming molten mixtures rich in silica, iron, magnesium, and dissolved gases. Each ingredient changes how the melt behaves, whether it will be runny and fluid, or thick and pasty. You don't need the formulas. You can feel the difference instead. Imagine two bowls. One holds warm syrup that pours easily. The other holds thick caramel that moves reluctantly. Both are liquids, but each carries a different mood. Magma is like this. Some flows far and wide. Some barely creeps. Beneath supervolcano regions, the magma is often thicker, richer in silica, which makes it more resistant to flow. Thickness means bubbles have a harder time escaping. And bubbles, down here, are made of gas, water vapor, carbon dioxide, sulfur compounds, all dissolved into the molten rock like invisible breath. You picture a sealed bottle of sparkling water. When closed, the gas stays hidden. When opened, bubbles appear and rise. Magma holds its bubbles the same way, quietly, invisibly, until pressure changes allow them to grow. But for now, everything remains contained. Held. Balanced. The heat source below comes partly from Earth's formation, the ancient collisions that built the planet grain by grain. Some heat also comes from radioactive decay, atoms gently rearranging themselves and releasing energy in the process. It is a slow glow, like embers that never quite fade. This warmth moves upward through the mantle in convection currents. You can think of convection like a lava lamp in extreme slow motion. Material warms, becomes slightly lighter, and rises. As it rises, it cools, becomes heavier, and sinks again. No hurry. No sharp edges. Just circulation. These currents help transport heat toward the crust, where partial melting can begin. Not everything melts, only certain minerals first, creating pockets of magma within still solid surroundings. Melt and crystal coexist, like slush forming in spring thaw. You float beside one of these regions now in your imagination. A magma body rests in a chamber, not an empty cave, but a sponge-like zone of partially melted rock and crystal framework. It is more like a glowing mush than an underground lake. Edges blur. Boundaries soften. Time behaves differently here. On the surface, you measure change in minutes and hours. Down here, change is measured in thousands of years. A chamber may grow a few centimeters in a year. Crystals may take centuries to fully form. Bubbles may wait decades before rising a measurable distance. Slowness is the rule. Slowness is the comfort. You notice how your own breathing has matched this deeper rhythm, longer inhales, softer exhales, as if your body understands ancient pacing when invited. Heat transfers outward from magma into surrounding rock. This can create hydrothermal systems, networks where groundwater seeps down, warms, and rises again carrying dissolved minerals. When it reaches the surface, it becomes hot springs, fumaroles, mud pots, geysers. The colorful pools you see in volcanic regions are chemistry paintings, minerals crystallizing from hot water like quiet art. So even when magma never erupts, it still paints the surface in warmth and color. Movement continues inside the chamber. New melt arrives from below. Some cools and crystallizes along the edges. Density changes cause gentle internal circulation. It is like a pot of thick soup kept warm, convection stirring slowly without boiling. You are often taught to imagine volcanoes as explosive moments. But most of their life is not eruption. Most of their life is preparation and adjustment. Quiet rearrangement. Subtle chemistry. Gradual heating and cooling cycles. Process, not drama, is the dominant story. You rest in that thought. Scientists study these systems by reading signals, tiny earthquakes caused by rock adjusting under stress, changes in ground height measured by satellites, shifts in gas composition escaping through vents. Each signal is like a syllable in a long sentence. No single syllable tells the whole story. But patterns do. Patterns are soothing. Patterns mean the earth is understandable. You picture magma again, glowing, viscous, mineral-rich, moving not like a predator but like weather in slow stone form. It does not chase. It responds. It follows gradients of pressure and temperature the way rivers follow slopes. If it rises because physics guides it. If it pauses because balance holds it. Nothing here is angry. Nothing here is personal. You let the glow become softer in your mind, more amber than red, more hearth than flame. This is inner warmth, not wildfire. Planetary metabolism rather than destruction. Earth digesting and renewing its crust from below. Pressure is always present here, like an invisible hand resting everywhere at once. And as magma gathers and thickens and warms, that pressure is quietly learning how to speak. You settle deeper into the underground quiet, where nothing rushes and nothing shouts. Here, change does not arrive like a storm. It gathers like a held breath. You can almost feel it, not as fear, but as fullness. A sense of something gradually becoming more. Pressure is simply force spread across space. But instead of thinking of equations and units, you imagine it as a gentle, constant hand resting on every surface at once. Deep underground, that hand is heavy. Rock presses on rock. Heat presses outward. Gases press in all directions, seeking a little more room. And yet, for long ages, everything holds. You picture the magma chamber again, warm, glowing, thick as melted sugar. Inside it are crystals forming and dissolving, like snowflakes appearing and vanishing in reverse. Mixed within the melt are gases, water vapor especially, along with carbon dioxide and sulfur gases, each one once locked inside solid minerals, now freed by melting. Gas inside magma is like air inside dough. When dough is first mixed, bubbles are tiny and trapped. As it warms and reacts, bubbles grow. The dough stretches to hold them. Underground, magma behaves in a similar way. As temperature shifts or new melt arrives, dissolved gases begin to separate into bubbles. Each bubble is small, but each adds to the internal push. You imagine millions of microscopic spheres, each one pressing outward with delicate persistence. This is how pressure begins to learn its voice, not through violence, but through accumulation. The surrounding rock is strong, but not perfectly rigid. Under enough stress, even solid stone bends slightly. You've seen thick plastic flex under weight. Rock does something similar when heated and stressed over long periods. It deforms slowly, a behavior scientists call ductile, meaning it changes shape without snapping. You don't need the term. You can feel the idea, strength with softness over time. But rocks closer to the surface are cooler and more brittle. They behave more like glass than wax. They can hold until they crack. And when they crack, they release energy in tiny pulses. These pulses travel as vibrations through the ground. You know them as earthquakes, but here they are often too small to feel. Only instruments notice them. You sit beside one of these instruments in your imagination, a seismometer delicate as a listening ear. It does not see. It does not predict. It listens. When rock shifts by even a fraction of a millimeter, the instrument draws a small trembling line. One tick. Then another. A pattern begins. The earth is writing in tremors. Most of these signals are minor adjustments, like a sleeper turning gently from one side to the other. Pressure redistributes. Stress relaxes in one place and grows in another. This is not failure. This is maintenance. You feel comfort in that motion as adjustment, not catastrophe. Inside the magma body, changes continue. New melt injected from below brings fresh heat and fresh gas. Think of adding warm syrup into thicker caramel. The mixture shifts, loosens, reorganizes. Temperature differences create slow internal currents. Crystals may partially melt again. Chemistry evolves like a recipe still being stirred. Pressure responds to every change in volume. If more melt arrives, space becomes tighter. If gas bubbles grow, they demand room. If surrounding rock cools and contracts, pressure redistributes again. It is a constant negotiation between contents and container. You picture a vast underground conversation without words. Scientists describe this using the language of stress and strain. Stress is the push. Strain is the shape change that follows. But instead of technical terms, you imagine a mattress. When you press your hand into it, that is stress. The dip that forms is strain. Remove your hand, and the surface slowly rises again. Rock, given enough time, behaves like that mattress. Sometimes pressure opens tiny fractures, hairline pathways no wider than a thread. Gas and melt may slip into them, moving upward in narrow sheets called dikes or sills. These are not yet eruptions. They are exploratory fingers, testing the architecture of the crust. Most freeze in place and go no farther. They become stone veins, hidden signatures of past movement. You run your awareness along one of these thin intrusions, a blade of once molten rock now solid, cutting across older layers like a bookmark in a closed volume. It tells a quiet story. Pressure once tried this path. Not all attempts succeed. In fact, most do not. That is another gentle truth you can rest with. The majority of underground pressure releases are partial, incomplete, self-balancing. Systems adjust before they break. Earth prefers small corrections over grand gestures whenever possible. Gas plays a special role in this balance. Gas is compressible. It can be squeezed into smaller space, unlike liquid melt or solid crystal. This means gas can absorb some pressure increase like a cushion. But if too much gas accumulates, the cushion becomes crowded. Bubble meets bubble. They merge. Larger pockets form. Larger bubbles rise more easily through thick magma, the way bigger air pockets rise faster in syrup than tiny fizz. Their upward drift changes pressure distribution again, subtly, steadily. You imagine watching a lava lamp where bubbles form, stretch, and glide upward through glowing fluid. No hurry. No panic. Just buoyancy doing its quiet work. Above the chamber, the ground itself may lift slightly, so slightly that only satellites can detect it. A few centimeters over months. A gentle swelling, like a sleeping chest rising. This uplift is one of the ways scientists know pressure is increasing below. The land becomes a slow signal. Even trees and lakes rise with it, unaware. You float upward in your mind and look down at this swelling landscape. Forests remain calm. Animals graze. Snow falls. The change is too gradual for ordinary senses. Only careful measurement reveals the motion. This too is soothing. Important processes often whisper. Pressure, then, is not an enemy here. It is a messenger. It tells scientists where melt is moving, where gas is gathering, where rock is adjusting. You return your attention to the chamber once more. It is fuller now than before. Warmer. More saturated with gas. Not dangerous in this moment, simply more prepared. Like clouds thickening before rain, not yet falling. Preparation is not outcome. Potential is not event. You let that distinction relax your thoughts. The deep system continues its patient work, heating, dissolving, crystallizing, pressurizing like a long symphony holding a sustained note. And when a note is held long enough, you begin to wonder not if it will end, but how. Somewhere ahead in Earth's memory, there are moments when the note changes, when pressure finds a pathway large enough to matter, and the sky itself begins to answer. But that comes later. For now, you rest beside the held breath, listening to the almost silence, where pressure is still deciding what it wants to say next. You rest now at the edge of deep time, where memory is not written in ink but in stone, ice, and quiet layers of dust. The earth keeps journals, though it never uses paper. It writes with ash. It records with chemistry. It bookmarks its great moments in sediment and glacier cores, waiting for patient readers. Tonight, you are one of those readers. You begin not with the eruption itself, but with the morning before. Imagine a landscape long ago, forests breathing, lakes still, animals moving through grass under an ordinary sky. Nothing in the air announces what is coming. No countdown appears. The planet does not use alarms. Its changes arrive when preparation is complete. Beneath that peaceful ground, pressure has been gathering for a very long time. Magma rich with gas. Rock stretched thin. Fractures mapped by stress. The system has reached a point where holding and releasing are almost equal choices. You stand in imagination at a safe distance, far enough to observe without fear, close enough to feel awe. The ground trembles, not sharply, but continuously, like a wagon rolling far away. This is not a crack of sound but a rolling vibration, a low note sustained. Then the surface opens. Not always as a mountain peak exploding, but sometimes as a widening ring, a great circular fracture miles across. The crust collapses inward as underground support empties upward. This structure is called a caldera, but you can think of it as a vast stone bowl forming as material leaves below. The eruption column rises not like a flame, but like a pillar of storm cloud made of rock and gas. It climbs higher than weather, higher than passenger planes. Hot ash and fragmented magma are blasted upward by expanding gases, forming a towering plume that spreads at the top like an umbrella. From afar, it looks almost soft. A gray-white tree growing into the stratosphere. You watch in calm slow motion. Particles rush upward, but your perception is gentle, buffered, dreamlike. Each grain of ash is tiny, many smaller than flour, formed when magma shatters into glass-like fragments during violent decompression. These fragments are not burned rock. They are exploded melt, frozen mid-flight. The cloud spreads outward and outward, carried by high-altitude winds that never sleep. Jet streams, fast rivers of air, take hold of the ash and begin to carry it across continents. The journey is swift by atmospheric standards, yet still graceful when viewed from far above. You rise with the plume in your imagination and drift with it. Below, sunlight begins to change. Not darkness, not night, but a whitening, a thinning. The sky turns milky. Shadows blur at the edges. The sun appears as a softer coin behind frosted glass. Light is being scattered by suspended particles. Each grain of ash and each droplet formed from volcanic sulfur reflects and redirects sunlight in many directions. It is like billions of microscopic mirrors floating overhead. This is not instant global change, but gradual spread. First regional dimming, then wider veiling as circulation continues. The atmosphere is layered like a calm ocean turned upright, troposphere below, stratosphere above. When eruption columns reach the stratosphere, particles can remain suspended for months or even years because there is little rain there to wash them out. So the veil persists. You feel the temperature response as a slow exhale. Not a freeze, not a shock, but a gentle downward drift. A fraction of a degree at first. Then more. Climate is sensitive to sunlight balance. When incoming energy dips, even slightly, average temperatures follow. Summers soften. Winters lengthen their reach. Scientists call this volcanic forcing, but you can think of it as a planetary parasol opening. You walk quietly through this altered light. Plants still grow, but more slowly. Some crops struggle where seasons become shorter. Skies produce more vivid sunsets because particles scatter red wavelengths beautifully. Evening colors deepen crimson, copper, violet, painted by airborne minerals. Beauty and difficulty coexist, as they often do in nature. You kneel and pick up a pinch of fallen ash in your imagination. It feels like powder between your fingers. Soft. Fine. Not heavy like sand. Volcanic ash is sharp under magnification, tiny glass shards, yet when settled thickly, it can blanket landscapes like gray snow. Over time, this ash becomes something else. Rain mixes it into soil. Minerals dissolve. Nutrients are released: phosphorus, potassium, trace elements plants crave. In the long arc, destruction feeds fertility. Many of the world's richest farmlands sit on ancient volcanic deposits. The earth recycles even its most dramatic moments. You move forward in time slightly. The eruption has ended. The column has fallen. The caldera rests, steaming gently. Lakes will someday form here. Forests will return. Animals will cross the basin without knowing its history. Recovery is not hurried, but it is reliable. Patterns of cooling show up in tree rings, narrower growth bands marking harder seasons. Ice cores capture sulfate layers like thin white lines, timestamps of atmospheric change. Ocean sediments record microfossil shifts. The planet's memory system is detailed and distributed. No single archive holds the whole story. Together, they speak. You sit beside a scientist in a quiet laboratory, watching them examine an ice core cylinder under soft light. Each layer is a year of snowfall compressed into crystal record. A spike in sulfate appears, evidence of a great eruption long past. No eyewitness needed. Chemistry remembers. This too is comforting: truth can be stored gently. Supereruptions are rare, separated by tens or hundreds of thousands of years. Rarity matters. It is part of the calm perspective. These are not seasonal storms. They are deep time events. Humanity measures history in thousands of years. Supervolcano cycles often measure in longer spans. You let rarity slow your heartbeat. The pale sky phase does not last forever. Particles settle. Rain cleanses the lower atmosphere. Stratospheric aerosols gradually fall or chemically change. Sunlight strengthens again. Temperatures recover. Climate finds a new balance, as it always does. Balance is not a fixed point. It is a moving center. You look up once more at the softened sun behind its mineral veil. Not frightening now, only different. Filtered. Muted. Like a lamp behind linen. The world has known many such dimmings and still continues its long story of oceans, forests, and breathing creatures. And as the sky slowly clears in your mind's eye, another question drifts toward you like ash on high wind: how far can a single grain travel when the whole atmosphere becomes its road? You lift your attention gently upward now, following one tiny grain of ash, no larger than a speck of flour, as it rises into the wide, invisible architecture of the sky. You do not rush with it. You float beside it, unhurried, as though gravity itself has softened for the night. The grain is light, but not weightless. Its journey depends on size, shape, and the currents that hold it. Larger fragments fall back quickly, settling near their volcanic source like heavy snow. But the finest particles, the ones ground nearly to dust, can remain suspended. These are the travelers. You ride with one now. At first, it climbs inside the eruption column, lifted by heat. Hot air rises because warmth spreads molecules farther apart, making the air less dense. Cooler air sinks. This simple rule, warm rises, cool falls, powers much of the movement in both weather and volcano plumes. Convection is the elevator of the atmosphere. The ash grain spirals upward in this rising column, surrounded by countless others. Collisions happen softly. Charges build from friction. Tiny sparks sometimes flicker inside great plumes, volcanic lightning, but you observe from far away, where everything appears muted and dreamlike. Soon, the grain reaches high altitude, where the eruption column spreads outward like the top of a tree. Here it meets fast-moving winds that circle the planet continuously. You can think of these winds as high-sky rivers, narrow, powerful bands of motion called jet streams. They do not flow randomly. They follow temperature contrasts between warm and cold air masses. Where contrast is strong, wind accelerates. Earth's rotation curves their paths into long, looping highways. Your ash grain merges into one of these highways. You drift along with it, watching continents pass below like slowly turning pages. Mountains wrinkle the surface. Oceans reflect faint light. Cities glow softly at night. Yet up here, borders mean nothing. The air connects everything. The atmosphere is layered, like a calm sea turned vertical. Closest to the ground is the troposphere, the layer of weather, clouds, and daily winds. Above it lies the stratosphere, drier, more stable, more stratified. When fine ash and sulfur gases reach the stratosphere, they can remain for a very long time, because there is little vertical mixing and very little rain to wash particles out. Rain is the great cleaner below. But above, particles linger. Your grain has reached this quieter layer now. Motion continues, but it is smoother, more horizontal. Instead of tumbling in storms, it glides in streams. Days pass. Then weeks. Still it floats. You notice something subtle. The grain is not alone anymore. It has become a nucleus, a tiny surface where chemical reactions occur. Volcanic sulfur dioxide gas, released during eruption, slowly transforms through atmospheric chemistry into sulfate aerosols, microscopic droplets that form around particles like your traveling grain. Think of it like dew forming around a seed. These sulfate droplets are especially good at scattering sunlight. Their size is just right to redirect incoming solar rays back towards space. Not all of them, just a small fraction, but enough that, when spread globally, the effect becomes measurable. A thin reflective veil forms around the planet. You watch sunlight touch this veil and scatter into softness. Down below, a morning begins slightly dimmer than it would have been. Not dark. Just filtered. The difference might be invisible to a casual glance, yet instruments will record it clearly. Science often sees what senses cannot. The ash grain continues its journey. Winds curve north, then south. Pressure systems guide motion like invisible shepherds. Some particles circle the globe more than once before settling. The Earth is round, and the air remembers that shape in its pathways. You begin to feel how connected everything is. A single eruption in one region can send particles across oceans, across hemispheres. Ice cores in polar regions record eruptions from faraway volcanoes. Antarctic snow remembers tropical mountains. Greenland ice remembers distant fire. The planet shares its stories widely. You pass through thin cloud layers where ice crystals grow in geometric hexagons and needles forming silently around microscopic seeds. Some ash particles help clouds form by acting as condensation nuclei, tiny platforms where water vapor can gather and become droplets or ice. In this way, volcanic particles sometimes help build clouds themselves. Seeds of sky architecture. Time stretches gently here. Your grain has been traveling for months now. Gradually, gravity regains influence. Collisions make the particle clumps slightly larger. Moisture adds weight. The downward drift begins not as a fall, but as a slow settling, like dust in a sunbeam. You follow it downward through softer air. Weather resumes its influence, updrafts lift it again briefly, then release it. Eventually, it descends through a light rain. A droplet captures it. The journey ends on a leaf in a forest far from its origin. No sound marks its arrival. Rainwater dissolves some of its minerals. The rest joins the soil. Years later, roots will absorb what remains. Stone will become leaf. Leaf will become breath. Breath will become life. The cycle closes quietly. You sit with that transformation, eruption to atmosphere, atmosphere to soil, soil to growth. Nothing is wasted. Matter only changes address. Scientists model these journeys using atmospheric circulation equations and satellite measurements. They release harmless tracer particles and watch how winds carry them. They map aerosol layers using lasers bounced from orbit. The tools are precise, but the principle is simple: the sky moves in patterns. Patterns bring calm to complexity. You look again at the global wind belts, trade winds near the equator, westerlies in mid-latitudes, polar easterlies near the poles. 3 great circulation cells per hemisphere, like slow-turning gears. Heat differences drive them. Rotation shapes them. Together they form the breathing system of the planet. Your ash grain traveled inside that breath. And now, as it rests in new soil, you begin to wonder about the sunlight it helped scatter, how a floating veil of mineral and sulfate can gently turn down the brightness of day, and cool a world not with shadow, but with reflection. You rest your attention now in the space between sunlight and sky, in that invisible meeting place where energy arrives and decisions are made. Every day, light from the sun travels across empty space and reaches Earth in a steady stream. It does not choose where to land. It simply arrives. What happens next depends on what it meets. Tonight, you watch that meeting happen slowly. Imagine a sunbeam entering a quiet room through a window. If the air is perfectly clean, the beam is nearly invisible. But if a little dust floats in the air, suddenly the light reveals itself: soft rays, glowing paths, gentle illumination of each drifting speck. Volcanic ash and sulfate aerosols turn the whole atmosphere into that quiet, dusty room. After a great eruption, sulfur gases rise high and transform into tiny sulfate droplets far smaller than grains of sand, smaller even than pollen. These droplets and fine ash particles spread through the upper atmosphere, forming a thin, global mist. Not thick like a storm cloud. Not dark like smoke. More like a transparent silk scarf wrapped loosely around the planet. You picture Earth wearing a luminous veil. Sunlight arrives as always, waves of energy moving at the fastest speed anything can move. When these waves meet particles in the air, Some pass through, some are absorbed, and some are scattered, redirected in new directions. Scattering is like a gentle bounce. Not destruction, just a change in path. Each tiny particle becomes a miniature mirror. Not a perfect mirror, more like frosted glass sending light sideways, upward, and back toward space. When enough particles are present, the total reflected portion becomes meaningful. A small percentage of sunlight never reaches the ground. It is turned away softly. This is called increasing planetary albedo, but you don't need the term. You can feel the image instead, Earth becoming slightly more reflective, like wearing lighter-colored clothing on a warm day. Lighter surfaces stay cooler because they send more sunlight away. You watch photons, packets of light, arrive and scatter in countless directions. The process is silent. No sound accompanies reflection. No signal announces deflection. Cooling begins without drama. Temperature responds slowly because Earth is large and holds heat well. Oceans store warmth like deep reservoirs. Land releases heat gradually. Air mixes and redistributes energy continuously. So when incoming sunlight decreases even a little, the response unfolds like a long exhale rather than a sudden drop. Fractions of degrees matter here. You imagine a global thermometer drifting downward by one small mark. Then another. Growing seasons shift slightly. Snow lingers a little longer at high elevations. Nighttime frosts arrive earlier in some regions. The changes are gentle individually, noticeable collectively. Climate is an average, a long conversation between day and night, summer and winter, ocean and sky. Volcanic veils change the tone of that conversation for a while. You float above the planet and watch sunlight strike cloud tops. Clouds already reflect a portion of incoming light, bright, billowing shields. Aerosols can make clouds form more easily by giving water vapor more surfaces to condense upon. With more, smaller droplets, clouds can become brighter and more reflective. Seeds of brightness multiply. This is called the cloud albedo effect, but again, you keep the feeling instead of the phrase, more mirrors in the sky. Not sharper, softer. A diffused glow instead of direct glare. You notice how calm this mechanism is. No moving parts. No engines. Only geometry and probability. Angles of incidence. Particle sizes. Wavelength interactions. Physics working like quiet choreography. Different wavelengths of light scatter differently. Shorter wavelengths, blues and violets, scatter more easily, which is why the sky is blue in ordinary times. Add more particles, and scattering increases across more colors. Sunsets grow deeper, redder, more layered, because long paths through particle-rich air filter light like stained glass. Beauty increases even as energy decreases. You walk through one of these filtered sunsets in your mind, copper light across water, rose-colored clouds, a dimmed sun large and gentle near the horizon. Painters once captured such skies after historic eruptions without knowing the cause. Art recorded atmospheric chemistry before instruments did. Observation comes in many forms. The cooling influence of volcanic aerosols has been measured many times. After well-documented eruptions, global average temperatures dipped for a year or two. Not catastrophically. Noticeably. Enough for careful instruments and patient scientists to confirm the link. Evidence arrives as patterns across datasets, thermometer records, satellite radiation measurements, ocean heat content, tree growth rates. Independent signals agreeing softly. Agreement builds trust. You sit beside a climate modeler in a quiet office at night. On their screen, equations simulate energy flow, incoming solar radiation, outgoing infrared heat, reflection, absorption, convection. Prediction through understanding. But models are not magic. They are structured stories, physics written in mathematical language. Their power comes from grounding in measurement. Volcanic eruptions provide natural experiments, real-world tests of how sunlight filtering changes temperature. The planet runs the experiment. Scientists read the results. You feel again how thin the active layer of climate really is, a fragile envelope of air wrapped around a rocky sphere. Most weather happens in the lowest slice. Most sunlight interactions occur before light travels more than a few dozen kilometers into that air. A thin stage for such important effects. Thin does not mean weak. Thin can still be powerful, like the lens of an eye focusing an entire world. The aerosol veil does not stay forever. Particles slowly fall. Chemical reactions change droplet size. Circulation moves material into regions where removal is easier. Over months and years, the filter fades. Reflection decreases. Sunlight returns to previous strength. The veil lifts gradually, like morning fog. You rest in that temporary nature. Cooling is not permanent. It is a phase. A response. A chapter, not the whole book. Earth adjusts continuously, feedback after feedback, seeking moving balance. And as you watch the last scattered rays soften across the curved horizon, another gentle question forms: what happens to seasons when sunlight is filtered, and how does summer learn to grow quieter without disappearing at all? You rest now inside a softened year. The calendar still turns. Days still lengthen and shorten. The sun still rises in its familiar arc. Yet something in the pattern has changed, not removed, not broken, only muted, like a melody played through cloth. The light that reaches the ground has been gently filtered, and the seasons respond in kind. You begin with summer. Summer is not erased by volcanic veils. It is reshaped. Think of a lamp with a dimmer switch turned slightly down. The room is still lit, still warm enough to see and move, but the intensity has eased. After major volcanic aerosol spread, average surface temperatures can dip enough that summer heat does not climb as high or remain as long. You walk barefoot through this quieter summer in your imagination. The air is mild. Heat waves are fewer. Nights cool more easily. The difference is subtle day to day, but meaningful across months. Climate is not one afternoon. It is the average of many. Plants feel this change not as disappointment, but as instruction. Growth depends on sunlight, temperature, water, and carbon dioxide. When sunlight is slightly reduced and warmth slightly lowered, growth rates adjust. Leaves still open. Photosynthesis still works, the quiet chemical miracle where light becomes sugar, but the pace slows. You picture each leaf as a small green laboratory, powered by photons. Fewer photons arrive. Production continues, just more gently. In some regions, this matters more than others. High-latitude areas, places already near the edge of warmth, are especially sensitive to small cooling shifts. There, a shorter warm season can reduce how long crops can grow or how far tree lines can advance. Snow may melt later and return sooner. The margins feel the change first. You kneel beside a field in your mind and watch the timeline of a plant. Sprouting begins a little later. Flowering arrives, but with less accumulated heat. Seeds still form, though sometimes fewer. Not failure, variation. Living systems are flexible within ranges. They bend before they break. Flexibility is a form of intelligence. Forests respond too. Trees build one growth ring per year, a circular memory written in wood. In cooler post-eruption years, rings grow narrower. Scientists can read these rings centuries later, matching narrow bands across many trees to identify years when summers were muted globally. Trees keep climate diaries without knowing they do. You walk through such a forest now, tall trunks, quiet shade, and imagine each ring as a whisper. This year was cooler, this year was dimmer, this year the sun arrived softened. No drama carved into bark. Just measurement through patience. Animals respond through timing. Migration schedules shift slightly. Insect emergence may move with temperature thresholds. Predator and prey adjust their calendars like dancers, subtly changing tempo to stay in step. Most ecosystems contain buffering capacity, diversity that allows reshuffling without collapse. Nature rarely depends on only one clock. You sit beside a lake at the edge of this gentler summer. The water surface warms more slowly. Thermal layers form later. Algae blooms may delay or reduce because light penetration changes. Each ripple carries physics within it: heat capacity, mixing depth, energy exchange with air. Water is a climate stabilizer. It absorbs change and releases it slowly. In agricultural history, there are recorded seasons after large eruptions when harvests were smaller in some regions. Not everywhere. Not uniformly. Climate effects spread globally, but outcomes remain regional, shaped by local soil, rainfall, and resilience strategies. Human communities adapt with storage, trade, crop diversity. Adaptation is also a technology. You breathe into that idea: adjustment rather than alarm. Cooling from volcanic aerosols is temporary, typically strongest for 1 to 3 years after a very large eruption. The atmosphere cleans itself gradually. Sunlight strengthens again. Seasonal patterns return closer to their previous ranges. Temporary does not mean trivial, but it does mean passing. You imagine the global energy balance like a set of scales. On one side sits incoming sunlight. On the other sits outgoing heat radiated back to space. Aerosols add a few extra reflective weights to the sunlight side, tipping the balance slightly toward cooling. When those weights fall away, equilibrium shifts back. Balance is dynamic, never frozen. Glaciers and high mountains may gain a little mass during these cooler intervals. Snowpack can increase. Rivers fed by meltwater may run differently the following year. Ocean surface temperatures dip slightly, influencing currents and weather patterns in gentle cascades of cause and effect. Climate is a web, not a line. You trace one thread: filtered sunlight to cooler land to altered evaporation to shifted rainfall patterns. Not everywhere, not evenly, but detectably. Scientists map these links using satellites, buoys, weather stations, and long records. Patterns emerge like constellations when enough points are plotted. Understanding grows from connection. Yet through all of this, the planet does not become alien. Birds still sing. Grass still grows. Children still feel warm afternoons and cool evenings. Experience continues, just tuned to a slightly different key. You let that reassurance settle in your chest. Soft summers are still summers. Light still feeds life. Warmth still visits the soil. The difference is in degree, not existence. In tone, not truth. You lie back in imagination under this filtered sky and feel how gentle change can be when spread across a world and across time. No single day carries the whole effect. It is distributed, averaged, woven through weeks like a subtle thread. And as you rest there, sensing how living systems adjust their rhythms to match available light and heat, another curiosity begins to glow. How do scientists notice these small seasonal shifts early, and what quiet instruments are always listening for the first hints of change beneath the ground? You return now from the wide sky to the patient ground, where listening becomes more important than looking. The deepest changes inside Earth rarely announce themselves with visible signs at first. They whisper through motion, through chemistry, through shape. And so, the people who study supervolcanoes learn first how to listen. You sit beside them in the quiet. There is no alarm bell ringing. No flashing red light. Only instruments, small, precise, attentive, spread across landscapes like thoughtful ears. Each one waits. Each one records. Together, they form a conversation between planet and observer. You begin with the seismometer. It is more delicate than you expect. Inside, a suspended mass hangs or rests in balance. When the ground moves, the frame moves with it, but the mass lags slightly behind because of inertia. That tiny difference becomes a signal. Motion becomes a line on a graph. A tremble becomes a pattern. You imagine it drawing Earth's pulse with ink made of time. Most of the signals it records are small, too small for human bodies to feel. Microearthquakes. Rock adjustments. Fractures relieving stress grain by grain. Around volcanic systems, these tiny quakes often cluster and migrate, tracing the movement of fluids and pressure underground like ants mapping tunnels. A swarm is not a shout. A swarm is a murmur repeated many times. Scientists look not just at how strong a quake is, but where it occurs, how deep, how often, and how its pattern evolves. One quake alone says little. A changing pattern says more. Data becomes meaningful through relationship, not isolation. You watch a scrolling seismic record, a soft jitter of lines, rising and falling. It looks almost like breathing. Next, you move to another kind of listening, deformation measurement. Instead of shaking, this is about shape. The ground above magma systems can rise or sink slightly as pressure changes below. Not meters. Not even decimeters. Often just centimeters, the thickness of a finger. Too small for eyes. Perfect for instruments. GPS stations anchored to bedrock measure their position constantly using satellites overhead. By comparing signals, scientists can detect if 2 points on the ground are moving closer or farther apart by very tiny amounts. A widening distance can suggest uplift, the land slowly doming as material accumulates below. You picture the earth taking a careful inhale. There are also tiltmeters, instruments that measure angle change. Imagine placing a marble on a smooth table. If the table tilts even slightly, the marble rolls. A tiltmeter senses that almost imperceptible tilt electronically. Around volcanoes, tilt patterns can reveal pressure changes like a level showing hidden slopes. Nothing dramatic. Just geometry speaking quietly. From the air and from orbit, radar satellites add another layer of awareness. They send microwave pulses down to the surface and measure the return time with extreme precision. By comparing repeated passes, scientists create deformation maps, color patterns showing where land has lifted or settled over weeks and months. It is like watching the ground breathe in slow color. You drift upward beside one of these satellites, circling Earth in steady rhythm. It does not worry. It does not predict. It observes. Observation is its only job, and it does it faithfully, pass after pass, year after year. Listening can be automated and still feel devoted. Now you turn to gas, the chemical voice of magma. Even when melt stays deep, gases can escape upward through cracks, soil, lakes, and hydrothermal vents. Carbon dioxide and sulfur gases are especially important messengers. Changes in their release rate or ratio can suggest shifts in magma supply or depth. Scientists sample gases at vents and hot springs. They also use spectrometers, instruments that read how gases absorb specific wavelengths of light, allowing measurements from a distance. A volcanic plume can be analyzed like a fingerprint made of molecules. Chemistry becomes language. You kneel beside a warm spring in your mind. Bubbles rise through mineral water. Each bubble carries information from depth, pressure conditions, temperature, melt composition. Nothing is wasted. Even a bubble is a report. Temperature sensors add another layer. Heat flow from the ground can increase when magma rises closer to the surface. Probes placed in soil and rock record long-term trends. Thermal cameras mounted on aircraft or satellites map subtle warming across wide areas. Warmth leaves signatures. You notice how none of these methods depend on a single clue. Science here is like assembling a mosaic. Seismicity, deformation, gas, heat, each tile incomplete alone, meaningful together. Agreement across methods builds confidence. Disagreement invites deeper study. Uncertainty is not failure. It is space for refinement. You sit now in a volcanic observatory control room at night. Screens glow softly. Graphs update in real time. No one is panicking. Most days, patterns remain within expected ranges. Monitoring is not crisis work, it is continuity work. Calm attention over long durations. Patience is the primary instrument. Supervolcano systems especially require long-term watching because their timescales are long. Years and decades of baseline data are needed to know what normal looks like. Only then can meaningful deviation be recognized. Without baseline, there is no anomaly. Knowing normal is a form of wisdom. You reflect on how similar this is to listening to your own body. You know your resting heartbeat, your usual breath rhythm, your typical energy. Because you know the baseline, you notice when something changes. Awareness begins with familiarity. Familiarity grows from gentle attention. Machine learning tools now help scientists scan vast data streams for subtle patterns humans might miss, correlations across sensors, early-stage trend shifts, signal clustering. These tools do not replace human judgment. They extend it, like additional senses made of mathematics. Mathematics becomes a quiet assistant. You feel reassured by the redundancy, many instruments, many methods, many teams across the world sharing observations. Knowledge is networked. No single watcher stands alone. Collaboration is part of planetary listening. The Earth is large. The listening is shared. And still, even with all this technology, prediction remains careful and probabilistic, not absolute. Scientists speak in likelihoods, scenarios, ranges. This is not weakness. It is honesty aligned with complexity. Systems with many variables require humble language. Humble language is restful language. You let that humility settle around you like a blanket. No one claims perfect foresight. Instead, there is steady watching, steady measuring, steady learning. A culture of attention rather than alarm. You look once more at the quiet instruments, the seismometer tracing tremors, the GPS station measuring millimeters, the satellite mapping centimeters, the sensor reading gases molecule by molecule, and you feel how listening itself can be an act of care. And as the screens continue their soft, tireless drawing of Earth's hidden motions, another gentle curiosity rises. How do scientists turn these signals into numbers and models that estimate how much cooling a veiled sky might bring? You drift now into a space where sunlight and temperature meet, where numbers describe reality as gracefully as poetry describes emotion. Imagine Earth as a large, living sphere, wrapped in blankets that absorb warmth, and mirrors that bounce some back into space. That is energy balance, the simple idea that the planet warms when it absorbs more than it releases, and cools when it releases more than it absorbs. Volcanic aerosols affect these blankets and mirrors. Sulfate particles reflect sunlight back into space, like millions of tiny silver disks floating above. Ash scatters rays sideways, softening the light that reaches soil, water, and forest. Even a small fraction of sunlight redirected can change the energy input enough to influence temperature globally. You picture photons, tiny packets of light, traveling toward Earth. Some strike clouds and bounce back. Some hit suspended ash and veer away. Others pass through and warm the surface. The balance among these paths sets the pace of warming and cooling. This is where mathematics whispers its role. Scientists describe these flows as equations: incoming radiation, outgoing radiation, absorption, scattering, reflection. But you do not need to see formulas to feel the meaning. Each equation is a story of movement, of energy choosing paths, of the Earth adjusting quietly in response. You imagine draping soft blankets over a glowing globe. Each blanket absorbs some warmth, each mirror reflects some light. Adding more reflective layers, volcanic aerosols, tips the balance. The blankets still exist, but the mirrors grow more prominent. Surface temperatures respond gradually, like a slow exhale. You move your attention closer to the surface. Oceans store heat more efficiently than land. Water has a high heat capacity, so small changes in sunlight cause gentle, delayed shifts in temperature. Land responds faster. Forests, deserts, fields each reacts according to specific absorption properties. Together, they integrate the subtle change from above. Climate models capture this integration. Picture a digital Earth made of grid squares stretching across continents and oceans. Each square tracks energy flows, temperature, moisture, and wind. When you add a layer representing volcanic aerosols, the model responds. Heat is absorbed differently. Surface temperatures drop slightly. Precipitation patterns adjust. Clouds respond. The model moves like a breathing organism. You float beside one of these simulations. Colors ripple across oceans and land. Blues deepen where cooling is strongest, greens and yellows adjust where light scattering shifts cloud formation. The planet in miniature obeys the same gentle rules as reality, only compressed in space and accelerated in time. You watch how delayed responses unfold. Cooling is not instantaneous. Some regions respond quickly, others slowly. Atmospheric circulation spreads effects globally. Oceans carry heat away and toward other regions, like conveyor belts moderating the temperature. Feedback loops amplify or dampen initial changes, some subtle, some more pronounced. Consider evaporation, for example. Cooler surfaces evaporate less water. Clouds form differently. Rain falls in new patterns. Soil moisture changes. Plants sense these changes and adjust growth rates. Ecosystems participate quietly in energy redistribution. Everything connects. Mathematics allows scientists to quantify this connectivity. Energy in minus energy out equals change in heat content. Each term is measurable. Incoming solar radiation can be observed from satellites. Outgoing infrared energy is mapped precisely. Surface heat content is sampled through ocean buoys and land measurements. Differences are small, but measurable. Small differences matter over large scales. You imagine each measurement as a note in a symphony. Alone, it is soft. Together, they form a melody that tells the story of cooling. You do not hear noise, you hear harmony. Some numbers and models are uncertain. The mathematics becomes a meditation. Each variable, each equation, is a gentle probe into nature's response. The planet's cooling after a volcanic eruption is a slow conversation between light and matter, absorbed and reflected, stored and released. You drift over imagined global maps, observing subtle cooling in high latitudes, slightly reduced surface heat near the tropics. These changes do not freeze the world, they modulate it. The rhythm of seasons continues, though adjusted. Summers are softer, winters a touch longer. Energy flows in waves, not jumps. You float downward toward one of the affected regions. A field of wheat grows. Leaves still photosynthesize, but slightly slower. Animals adjust quietly. Humans notice small differences in harvests and temperatures. No chaos, only adaptation to a world slightly dimmer, slightly cooler, temporarily changed by particles floating high in the sky. Reflection and absorption become sensory, not abstract. Mirrors in the sky, blankets on Earth, gentle adjustments across oceans and continents. The mathematics is the language that turns those subtle interactions into predictable patterns. It allows curiosity without fear, observation without panic, understanding without rush. You sit beside the model again, watching output graphs ripple gently, as though the planet itself were breathing in numbers. The soft descent of temperature, the gradual return to baseline, the pattern of diffusion, each element follows rules, yet still feels natural, calm, inevitable. And as the model stabilizes in your imagination, another question begins to take shape. How does life endure and adjust when the blankets thicken and the mirrors brighten? And how do ecosystems learn to continue their rhythm under skies dimmed for months, but never forever? You step into the world after the ash has settled, after the sky has lifted its veil, and feel the quiet pulse of recovery. The eruption's roar has passed. The clouds of gray and white have dispersed into the high winds or dissolved through chemical processes. Light returns fully to the land, though its journey has been softened by lingering particles. You breathe in the atmosphere, carrying whispers of sulfur and mineral dust, a subtle reminder that life always follows the retreat of fire. At first glance, the terrain seems stark. Fields lie blanketed under fine layers of volcanic ash, gray and powdery, like soft sand draped across hills and valleys. Trees are buried partially, shrubs flattened, streams carrying sediment downstream. The world feels hushed, as though Earth itself has paused to take stock. Yet beneath this quiet exterior, a complex symphony of renewal begins. Microbes are the first responders. Tiny organisms, invisible to the eye, awaken in the ash, consuming minerals, breaking down rock fragments, releasing nutrients. They create microhabitats for other life to follow. Each bacterium, each fungus, works as a chemist and architect, transforming what was inert into the earliest stages of fertile soil. The work is slow, patient, cumulative, not abrupt, not frantic. You imagine crouching close, watching a microscopic world flourish in a single grain of ash. There is no noise, no rush, only the gentle rhythm of metabolism and growth. Life starts here, quietly, like a slow heartbeat returning after a long pause. Plant life begins to appear next. Mosses and lichens, pioneers, colonize bare rock and ash. They anchor particles with thread-like structures, trap water, and add organic material as they live and die. The land is no longer sterile, it becomes a canvas for gradual painting in shades of green. Each new sprout is a signal of patience and resilience. Seeds buried before the eruption germinate when conditions allow. Nutrients released by ash, now partially dissolved into soil, feed them. Grasses emerge, softening the gray blanket. Flowers follow. Shrubs expand. Roots penetrate deeper with each passing season. The landscape slowly transforms from ashen gray to muted green, and finally to the brighter hues of thriving life. Animals return in tandem. Insects first, beetles, ants, pollinators exploring new niches created by changing plants. Birds follow, drawn to the abundance of insects and seeds. Mammals return cautiously, navigating altered terrain, yet finding familiar patterns of shelter and food. Nature remembers how to resume itself. It is as if life itself carries a quiet memory of place, of balance, of continuity. You float above the recovering land, watching this gradual pulse of restoration. Rivers run clearer as sediment settles. Lakes fill with nutrients slowly. Wetlands begin to form where ash is compacted, creating new habitats for amphibians and waterfowl. Forests expand from edges inward, each generation of trees building upon the soil created by the last. Time is the most important agent here. Recovery is not instantaneous. It is measured in years, decades, sometimes centuries. Yet the pattern is reliable. The planet's systems operate in loops: chemical, hydrological, biological. Each loop slowly smooths the scars of eruption. The more you watch, the more you see that even catastrophic events are absorbed and integrated by the patient rhythm of life. You consider soil formation itself. Ash contains minerals essential for growth: potassium, magnesium, calcium, which slowly mix with organic matter. Roots stabilize loose sediments, prevent erosion, and allow water to penetrate deeper. Microbial communities cycle nutrients in ways that build fertile ground for the next wave of plants. What was once destructive becomes generative. Humans, too, have observed these processes for millennia. Ancient civilizations farmed volcanic soils, noting that areas near long-extinct eruptions were unusually productive. They understood, in practical ways, the regenerative power of time, mineral-rich ash, and patient cultivation. Civilization itself learned to coexist with Earth's cycles, finding sustenance in places once scarred. You watch the cycle extend farther still. The ash is transformed, taken up by water, carried into oceans, feeding plankton, the tiny foundation of marine food webs. Life everywhere adapts, absorbs, and grows. Erosion, deposition, biological succession, nutrient cycling all become parts of a seamless choreography that returns balance to what seemed altered. You feel the lesson not only in the world outside but within yourself. Resilience does not always require immediate action. Recovery can be subtle, incremental. Patience is as powerful as effort. Healing occurs when systems, biological, geological, and human, are allowed the time and space to resume their rhythms. The landscape now appears alive in multiple layers: beneath your feet, in the soil, across the plains, in the grasses, above, in the birds and the returning trees. Even the air carries life, in microbes, spores, and pollen-riding currents that traverse continents. Recovery is multidimensional, simultaneous, interconnected. You notice how quiet this is. No loud declaration announces that the earth has healed. Change happens in whispers: a new leaf unfurling, a seed germinating, water flowing. Yet the cumulative effect is profound. What seemed destroyed becomes renewed. The world is never truly blank, only waiting to be rewritten. As you settle into this vision, your mind drifts across scales of time. One eruption, brief in comparison to geological history, leaves traces: ash layers in soil, chemical shifts in water, tree rings marking cooler summers. But the overall story continues. Life continues. The planet moves forward, carrying memory of events, yet never halted by them. You float gently above this renewed land, seeing small streams of light filter through young forests, noticing how life emerges from what seemed inert. Recovery is patient, unhurried, and natural, a rhythm to match the cycles of the planet itself. And as the scene stretches infinitely into forests, fields, and rivers, you sense another quiet question beginning to take shape: how does the earth remember these events, and how do its slow memories guide its living systems toward balance across centuries and millennia? Chapter 11: The Long Memory of the Planet. Chapter summary: you reflect on how Earth records its own history in rock, ice, and sediment. Layers become pages in a slow, unfolding diary. Chemical signatures tell stories of climate, eruption, and life. The past is readable, offering quiet guidance to the present. Memory itself becomes a source of calm understanding. You drift now beyond the immediate recovery of life and air, deeper into time itself. Earth remembers. It carries the quiet, persistent record of its own history in stone, ice, and sediment, much like a patient scribe keeping notes for an audience centuries away. You imagine turning page after page of a diary written in mineral and crystal, in isotopes and tree rings, in frozen bubbles and layers of ash. Start with rock. Layers of volcanic deposits, sedimentary strata, and metamorphic formations hold encoded memories. A single layer of ash from a supervolcano tells not only where and when the eruption occurred but hints at the magnitude of force, the composition of the magma, even the prevailing winds of that ancient moment. These pages are written in texture, color, and thickness, a language both physical and precise. You trace your fingers along a sequence of strata in imagination. Each band is a sentence. Each mineral grain, a word. Chemical composition serves as punctuation. Layers tell a story of eruption, cooling, sediment deposition, and sometimes erosion. Millions of years of history are stacked quietly beneath your feet, waiting to be read. Ice too becomes a living archive. In polar regions, snow accumulates year after year, layer upon layer, compressed slowly into dense ice. Each layer traps air bubbles, tiny pockets of atmosphere frozen in time. Those bubbles contain carbon dioxide, methane, sulfur compounds, whispers of climate long past. Scientists extract ice cores and slice them carefully, like opening letters written by ancient skies. The timing of each layer is remarkably precise. Seasonal changes leave subtle differences in texture, dust content, and chemical concentration. Volcanic eruptions leave thin dark layers in the ice, often only millimeters thick, yet their presence signals global events, reaching far from the source of fire and magma. Sediments at the bottom of lakes and oceans are another archive. Layers of silt, organic matter, and ash accumulate gently over centuries. Microfossils, tiny shells, pollen grains, and other remnants of life settle along with mineral particles, preserving snapshots of climate, vegetation, and environmental change. Each layer is a memory waiting for patient hands and attentive eyes. You follow a journey through these archives. One layer shows a cooler year, indicated by higher concentrations of sulfate. Another reveals a subtle drought, recorded by pollen absence. Yet another preserves a flood, marked by thick sediment washed from distant hills. All of these fragments form a continuous narrative, readable if only slowly, with care. Chemistry acts as translator. Ratios of isotopes oxygen, carbon, nitrogen carry precise information about temperature, precipitation, and atmospheric composition. Trace elements reveal nutrient availability, volcanic inputs, and even ocean currents. With each chemical fingerprint, Earth speaks. You simply have to listen. You imagine sitting in a quiet laboratory, instruments arrayed like attentive listeners. Samples are sliced, scanned, measured. Tiny variations become lines on graphs, patterns emerge, connections are drawn. What at first appears random now appears meaningful. Repetition builds confidence. Evidence confirms the story told by multiple independent sources. Memory is not passive. It interacts with life. Plants respond to climate cues preserved in soil composition. Rivers follow paths guided by topography formed over millennia. Microbes metabolize minerals previously laid down in ancient eruptions. Life and memory interweave in ways that sustain the planet. Even short-term events, the ash from a supervolcano, a brief cooling of summers, a temporary increase in sulfate aerosols, leave marks in these archives. They are minor strokes in the long painting of geological and ecological history, yet each can be identified by careful reading. You sense the comfort in this. The planet's long memory reassures. Events do not vanish without trace. Knowledge of the past provides perspective. Modern eruptions, weather anomalies, and climate trends can be interpreted against the backdrop of centuries and millennia of experience. Each measurement becomes meaningful, each observation contextualized. You float along a timeline, visualizing layers like a staircase descending into Earth's memory. Some steps are thin, representing single years. Others are thick, containing decades of accumulation. The further down you go, the more distant the story, yet the pattern remains intelligible. Nothing is lost, it is only folded into new forms. Human beings, in their own short histories, rely on these layers for insight. Ice cores guide climate models. Tree rings inform agricultural planning. Sediment records warn of flood risks, erosion trends, or volcanic hazards. Memory of the planet supports foresight, turning observation into understanding. You feel the calmness that arises from knowing that the Earth does not forget. It is patient. It records carefully, continuously, without panic or haste. Time itself acts as a gentle editor, integrating disruptions into broader narratives, smoothing extremes, but preserving detail. Even catastrophic events are woven into continuity. As you trace the story of memory, you recognize a rhythm: eruption, fallout, deposition, growth, erosion, preservation. Life responds. Earth responds. The dialogue between geological processes and living systems unfolds over centuries. Observing this interplay, you perceive cycles, not chaos. Patterns, not random shocks. The planet's memory offers reassurance as well as knowledge. And as you settle into this vision, feeling the soft weight of past events beneath the present moment, another gentle thought begins to form: if Earth remembers, then what does it reveal about the balance between activity and stillness, eruption and calm, now and the next sleeping giant waiting beneath your feet? You settle once more on the familiar ground, your body feeling its weight, your breath syncing with the rhythm of the world around you. Beneath the soil, deep beneath the mountains, the supervolcanoes sleep, not gone, not threatening, simply patient. You sense them as part of a larger rhythm, a slow heartbeat of the planet, invisible yet profoundly present. The Earth is alive, but not hostile. Its power is not meant to frighten, only to remind. You have walked through its mechanisms, molten rivers flowing like honey beneath the crust, pressure building imperceptibly over centuries, ash veiling the sun in cooling summers, life recovering grain by grain, and the long memory written in rock, ice, and soil. Each piece fits into a vast, interwoven system that balances creation and destruction, growth and pause. You feel the intimacy of this understanding. Knowledge is a soft lens that allows you to see the planet's cycles without alarm. It turns what might have been terror into curiosity, what might have been worry into calm attention. You recognize that observing Earth is not about control, it is about presence, mindfulness, and respect. The air around you carries gentle reminders of cycles. Wind moves softly through trees. Streams murmur over stones. Clouds drift lazily across the sky. Even without eruptions, without dramatic events, life continues, with rhythms that are subtle and sustaining. You notice the quiet persistence of motion, the soil absorbing rain, the forest breathing in carbon dioxide and exhaling oxygen, the oceans circulating warmth. You reflect on the instruments you imagined earlier: seismometers, satellites, tiltmeters, gas sensors, all quietly listening, all serving as companions in understanding. Science becomes an act of care, a meditation extended over continents and years. You realize that watchfulness does not create fear, it creates connection, reassurance, and intimacy with the living world. Memory also lingers here. Every rock, every grain of ash, every tree ring carries its history. You rest knowing that the Earth's slow recollection is continuous and reliable. Events that seem monumental in a human lifetime are absorbed, integrated, and remembered without haste. The past provides perspective, the present provides grounding, and the future remains a space of wonder and possibility. Life, too, continues beside you. Plants stretch toward filtered light, microbes transform soil, animals follow seasonal rhythms, and humans adapt with patience and ingenuity. Each organism participates in the quiet symphony of survival, resilience, and regeneration. You feel the reassurance of continuity, that even when extreme events occur, systems have the capacity to recover, adapt, and flourish over time. You lie beside this living world, feeling a gentle rhythm beneath your body, subtle movements of the earth, the pulse of life above, and the infinite memory recorded in the rocks below. You realize that cycles replace suddenness, understanding replaces panic, and awareness replaces fear. The planet is not a threat, it is a companion. And as night deepens, your mind drifts softly into the thought that life, observation, and memory all exist together in harmony. The supervolcanoes sleep, the skies clear, the seasons continue, and you can rest in the presence of a world that is alive, balanced, and patient. Somewhere beneath the surface, deep and silent, Earth waits, not with malice, not with urgency, but with the quiet constancy of life itself. And you, lying beside it, feel the comfort of that rhythm, knowing that curiosity and calm, wonder and watchfulness, can coexist in perfect harmony as you drift towards sleep.